Hello. Matrix inverses. I suppose I should specify what kind of inverses. There's normally two different types. For example, let's just look at the first example of our matrices. Our numbers are one by one matrices, right? So I could talk about the additive inverse of this. Well, that would mean that I would add the number -5, and that gives me 0, right? And then there's also the multiplicative inverse of the number 5, which is, let's see, I need to multiply that by something, all right, which is 1/5, and I get 1. So there's additive inverses and multiplicative inverses that we would think about normally when we're doing mathematics. And these ideas tend to be, oops, I want to erase something here. These ideas tend to be very important for matrices as well. So we're going to focus on, well, I'll write it down just for completeness here. I'm going to write down the additive inverse. It's really easy to find an additive inverse of a matrix. Here's an example right here. Let's take the number, or the matrix 1, 2, 3, -1. And now when we say an additive inverse, what we're looking for is something to add to it so that we get back to what we call the zero matrix, which is this matrix, okay? And it's pretty clear what we would put in there. So the additive inverse of this matrix here is the matrix -1, -2, -3, and 1. See, when you add those together, you get 0, the zero matrix. Okay, so that's an important thing to be aware of, and a nice definition to have if we further study matrices, which many of you will. But the one that we need for our studies in this class is what's called the multiplicative inverse of a matrix. So the idea is the following: if you're given a matrix, let me write one down here. Okay, I'm going to put down 1, 2, 3, 4. The idea here is can we find a multiplicative inverse, that is some matrix here, such that when I multiply it together, I get what's called the identity matrix. And for our purposes, it's this. And it'll turn out that this matrix will be very important. And here's the notation that we use. If this is A, the thing that we're looking for is called A inverse. And we say that that's equal to the identity matrix. And I put a little 2 here to indicate that we're in a 2 by 2 situation. We don't normally speak of inverses of matrices that are not square, because for one thing, it just can't be done in a very systematic way. It can be, but we couldn't do the following. In fact, we couldn't multiply in different orders. I mean, you may realize this, that the only time you can multiply, if you have A times B, the only time that could even possibly be and both of these existing, right, is if they're square, essentially. Well, not square. I guess they could be. That's not true. I guess I could have a 2 by 3 times a 3 by 2, right? That would give me what kind of a matrix would that give me? A 2 by 2, 2 by 2. But if I multiply them in the other order, I would be having a 3 by 2 times a 2 by 3, and that would give me a 3 by 3. But you see, what we're really interested in here mostly are the situations where we have square matrices. So we're going to be considering square matrices in the rest of this talk here. So here we go. So there's our some examples. There's our one-dimensional identity. That's our two-dimensional identity, and this continues on with the three-dimensional identity here listed right here, and there's the four-dimensional identity matrix right there. I guess it's not really four-dimensional. I shouldn't say that. It depends upon what you mean by dimension. You would either say 4 or 16, depending upon certain things, so it's unimportant at this stage. But the idea is, a really important idea is that if you take a matrix and you multiply it by the identity matrix, you get that matrix back. And we'll see that this is a very important tool that we'll be using to answer some questions. That's why we're studying matrices. So here's the definition again of what the matrix is. I mean, what the identity matrix is. It's some matrix. So given A, we want to find some matrix that we can multiply by to get the identity, and vice versa. We want it to be what we would call both a right and a left identity inverse. And in fact, it will turn out that it will be the case in our situation. Yes. Okay. So here we go. Let's do this. Let's see. I'm going to show you a method or technique for actually finding the inverse of a matrix if it happens to exist. It may not exist, and I can show you some examples of that later. So here's what we're going to try to do. We're going to try to find A inverse if A is this matrix. And here's what we do. We go back to our old technique of the Jordan method, right? The Gauss-Jordan method. And what I mean by that is the following. Here's what we do. This works. There are many techniques for finding inverses, or let's say a couple or few, but this is the one that we'll be focusing on in this class. So we start out by step one. We basically write down the matrix A. Right? You can see here this is A, and then right next to it in an augmented form, we write the identity matrix. So here's A, and there's the identity matrix. Now our game will be it turns out we're going to use row operations, right, to get to a matrix that looks like this, where the identity matrix, right, is going to be sitting there, right? You see the identity matrix right there. And then we're going to see that there's another matrix, B. Well, guess what? It turns out that if you do this, that B that we're looking for actually is the inverse of the matrix A. So this is kind of a nice technique. And I could go through the details of showing why that's the case, but I think I'll just leave it as sort of a procedure, like an algorithm, like when you divide. You can check to see it's the inverse by simply multiplying the two together, and you'll see that. So let's just go through basically what we did to get from here to here. So I guess the first thing we did, let's see what happened from here to here. Well, we rewrote our first row. That just we left that the same, right? And then recall from when we worked with the Gauss-Jordan method in the past, to get rid of this 2 right here. I guess what we've done this. We take I guess we took row 2, or I remember I called it equation 2. I could put an R there. Row 2, and if I actually add to that minus, what did I do? Minus 2 times equation 1. Let's see if that's really what I did. It was either that or it was 2 times equation 1 minus equation 2. So let's see if that worked. But that's the idea. You see, take 1, oops, I've got this. Oh, no, here we go. So equation 2, so you see there's 2, minus 2 is 0, so that worked out. Then here we have minus 2, okay, minus 0 is minus 2. Now here we have minus 1, minus 2 is minus 3, and so on and forth. And you continue that here too. That's how the minus 2 comes here, and this 1 gets here, and this one here. So then you do just like you had done. So there's going to be a rule here to get this one, this row. Then you go to the next one, and you do your reduction. See here what we did is we put all zeros. In the first step we put all zeros here. The second step, look how we put a 0 here and a 0 here. In the third step we put zeros here and here. So you see what you're looking at here at this 3, 2, minus 3. That looks like a diagonal matrix. So to finish it off, what we do is we just basically take this and divide by 3. And then take this second row and divide by 2. Take the third row and divide by negative 3. And then there you have it. So you can go through, and I highly recommend, I'm purposely not telling you what's going on. You should go back and review this Gauss-Jordan method and see how you can get from here to here, because you'll be needing to do that on your own. And notice then we get this inverse, and lo and behold, we can check. Let's just actually, to see that is the inverse. Well, how do we do that? Let's find out. Let's just do our little multiplication thing. We get 1, 0, 1. Remember how we did our multiplication? Or at least this is how I like to do multiplication is to try to, it's being very messy here, right? But you can see, okay, let's just do it. If I take this one, 1 times 0 plus 2 times 0 plus 3 times 1/3, that really does give me a 1 here. Let's just check this first row. I better get a 0 here. So if I take 1 times a minus 1/2 plus, plus 2 times a minus 2, so that's minus 1/2 plus 1, and then 3 times 1/2. So let's see what I have here. I have minus 1/2, minus 2/2, then plus 3/2. So that really is 0. So what you'll notice if you go through the calculations like we had done in the past, you really will get the identity matrix right here. So that's how we can find inverses. Okay. Now let me show you how we're gonna solve this, these systems of equations using these inverses. It's really a nice thing, and it's based upon this. What you're looking at here, you have this situation that if we have a matrix equation AX equals B, right? Now look here, if I multiply both sides of the equation by A inverse, then look what I get. On the right-hand side of the equation, I get A inverse times B. Look what happens on the left-hand side of the equation. You get this A inverse AX. Then you get A inverse A, which is the identity, which is X. And look, that's how we solve our matrix equation. This should remind you, like, when somebody came up to you, really what we're at here is we're at this situation. The first time you saw this equation, 5 times x equals 4. And then they said, divide by 5. What they really should have said, I guess, is multiply by 1/5 on both sides. So then we get, that's the multiplicative inverse of 5. So we get 1/5 times 5x is equal to 1/5 times 4, and that's how we got our answer, right? So that is this calculation I'm doing on the right, which you did in I don't know, 8th, 9th grade, 7th grade, I don't know, whenever it was, maybe before that actually. That's exactly the calculation we're going to carry out now, except using matrices. So let's look at this example. Okay, here we have an example. Okay, so here's a business application, more or less, of this technique. Fertilizer. Okay, so we have three brands of fertilizer are available that provide nitrogen, phosphoric acid, and potash, right, to soil. And these are three important things that we need to add to soil to grow things, I guess. One bag of each brand, right, produces the following units of each nutrient. So here's our table, right? Here's our three nutrients, and here's our brands, and we can see that we have this brand, and this brand, right? So notice how they're slightly different. Okay, but here's the deal: for ideal growth of soil, what is this? On an Whoa, I erased something here. I'm sorry. I guess that would be, let me go down here. Kansas. Let's see. Oh, Michigan. That's Michigan. Okay. So our ideal of a Michigan farm we need 18 units of nitrogen, 23 units of phosphoric acid, and 13 units of potash per acre, right? The corresponding numbers for California farm, right, are different, right? You need, 31, 20, so different things. And for Kansas, you need even a different mixture, okay? So the question is, how many bags of each brand of fertilizer should be used per acre for ideal growth on each farm? Well, what does that mean? Now let's take a look at these equations here. So the first thing says, I guess we should say what we're going to do here. So you got X, Y, and Z. So I should tell you what these are. So X is going to be the number of bags of, that's bags of here, my pen isn't of this stuff. That's the first type. So here I'll put an X as this is X, the number of bags of that. The number of bags, Y is the number of bags of the big grow, right? And Z is the number of bags of this. So look what happens. So how much nitrogen do we get? Well, we take 1 times the number of bags, right? For this is the nitrogen equation, right? Nitrogen. We get 1 plus 2 times the number of bags of the big grow plus 3 times the number of bags of that, and you get A. So similarly, you get the equation for the phosphoric acid and for the potash here. Okay, so look at that. We have a nice system of equations, right? Now, what we can do and what we will do right at this moment is to transform this into a matrix equation, and there it is. Okay? Now, so here's our nice thing, right? We have this matrix A times X equals B, right? So what we're going to do is use our technique for finding the inverse. We're going to find A inverse. There it is. Oh, yeah, I mean, that took a little doing, right? We would carry out the operation of finding an inverse. And now we can find the solution. We know the solution to our equation here is that X is actually has to be equal to what? It's A inverse times B. And it's very critical that you have the A inverse on the left. You may try to search for some examples. There are, countless number of them, and actually an infinite number of examples where we have the fact that when you take A inverse times B, it's not equal to B times A inverse. So it's very critical that your multiplication is this way. A inverse B. A inverse is on the left. Because that's how we got the A to cancel over here when we multiply by the inverse on the left. Okay, so if you do that for the different choices, you would see that for Michigan, you would get 18 bags. So, for Michigan, B is equal to this 18, 23, 13 vector. So the answer is you need 5 bags of the first, 2 of the second, and 3 of the third. For California, you'd use 2 of the first type, 4 of the second type, and 7 of the next type. And for Kansas, you'd have to use 20 bags of the first type, 19 of the second, and 15 bags of the third. So you mix up these huge batches, you throw it into the old fertilizing device, and you start rolling down doing your crops there. So, okay, I hope that makes sense. And I highly recommend that you go through these in detail by, pausing the video and making sure you understand everything that's going on. And if you have any questions, please contact me, and I'll do some more for you.